right. My name is Zach Shuret-Quanti, and I'm a research associate at the Turing Institute in London. And I'm also joined by Andrea Pizzaperato, who is a visiting researcher at the University of Bath. And today we also are joined with, remind me your name, sorry?
It's maybe that one.
Who has joined us as an enrichment student here at the Turing. So for those of you who are not familiar with the Turing Institute, this is UK's National Institute for Data Science and AI. Also, on a side note, if you're willing and keen to share your work within this remit, please feel free to get in touch with us and we could find the right slot for a seminar. So as for the format of the seminar, we'll start with a nice talk by Rudy, followed by Q&A, which you're free to do so through the chat or by asking in person. So without further ado, I would like to introduce Rudy Geelen. I hope I'm pronouncing that correctly.
That's pretty good.
Okay.
I'll take it.
Geelen, so we have Rudy Geelen today, who is a speaker for today. And just a bit about Rudy. So he's obtained his Bachelor of Science and Master of Science degrees in Mechanical Engineering from Eindhoven University of Technology in the Netherlands in Mechanics of Materials. He received his PhD in Mechanical Engineering and Material Science from Duke University in March 2020, focusing on computational simulation of pervasive fracture and failure and the development of scale bridging approaches based on state-of-the-art extended generalized finite elements techniques. Rudy is interested in the broad area of computational science and engineering with a strong focus on computational mechanics, model order reduction, and scientific machine learning. As such, his research is interdisciplinary both with respect to computational science domains and real-world engineering applications. Ongoing and past research has been on the development of high-performance computation models and methods in simulation-driven engineering for coupled problems of multi-scale nature. So with that, I thank you all and welcome Rudy to take the floor.
All right, thank you so much for the elaborate introduction, and thank you so much again to the organizers for having me this morning here. So today I want to talk about learning physics-based reduced order models from data using what we call quadratic manifold constructions. Before I get started, I do want to apologize for the heavy use of mathematics and mathematical notations in the slides. Typically, it's not recommended. But for the purposes of this work, it is pretty fundamental in nature. I had to resort to the use of a lot of equations. If you have any questions along the way, then please do interrupt me. Other than myself, for the work I'll be talking about today, I had a lot of valuable support from Stephen Wright at University of Wisconsin. He is one of the leading experts on numerical optimization, and Karen Wilcox, who is my mentor here at the Odin Institute and who also happens to be the director of the Odin Institute, who is an expert on reduced order modeling and multi-fidelity modeling of dynamical systems. I'll start off with a little bit of background into projection-based model reduction and the work I'll talk about today. We'll dive in the data-driven learning of these quadratic manifold constructions. We're going to switch gears then a little bit and talk about how these manifold constructions can be leveraged in the context of non-intrusive model reduction. I'll give you a brief demonstration of the approach on a set of numerical experiments. We'll talk a little bit about an extension that we're currently developing where we kind of apply this problem to nonlinear problems. And then I want to give you a little bit of an overview of what are some of the current and ongoing efforts in the group in the space of this manifold work. We have to recognize that physics-based models are very powerful and they bring in a lot of predictive capabilities, but they're computationally expensive. So these images are a little bit of a sampler of my PhD work at Duke University, where I was very much concerned, as the introduction already implied, with, the variational modeling of fracture in materials, the failure of materials in engineering structures, And what I found myself doing, especially in the later stages of my PhD, was, you develop a really great computational model. You have to change the model parameters, the input parameters a little bit. You have another expensive simulation that you kind of throw on the cluster, and you need to wait a couple of days to process the results and kind of repeat this process all over. So this really made me appreciate the notion of data-driven learning and model reduction, which has what led me to my appointment here at UT as a postdoctoral researcher. So as I mentioned, this brings us to the notion of reduced order modeling and data-driven learning, right? So starting point is the following. We start off with a high fidelity physics-based simulation, right? You have your favorite numerical code, whether it's solving, some kind of fluid problem, fluid structure interaction, and you're pure mechanical, whatever it may be. Typically, these problems are very large scale, right? Which means that in order to solve these systems, it takes hours, days, weeks, if not even longer. To those systems, we now want to develop good approximation that we're going to call a reduced order model that approximates the dynamics of these high fidelity systems, but at a fraction of the computational costs. In other words, we want to be able to solve these systems in a matter of seconds or possibly minutes. And this is exactly the outline of projection-based model reduction. And it really follows three active ingredients. We start by training, right? So we solve a set of PDEs to generate a set of training data that we're going to call the training snapshots. We are going to identify structure, right? So we're going to compute a low-dimensional basis to which these dynamics can be projected. And in the third and final step, that's the actual reduction step, where we do a projection of the PDE models onto this low-dimensional subspace that we have identified in step 2. A little bit of notation before I'm going to dive into the new technical contributions. Today we're going to be talking about these mappings. We're going to talk about, a high dimensional state S, right, at any given time, or parameter instance T, that is approximated as a linear or nonlinear transformation of ST, S hat T, in which S hat is the reduced states vector, right? If you talk about POD, this is essentially the POD coordinate vector, but you can think about it in a broader sense. N is the full order dimension of the model. R is the reduced basis dimension. So, this is some notation I'm gonna try to use consistently throughout my talk. Other important notation is that sref, we'll talk about it a little bit, is a reference state that we have introduced for shifting or centering our training data. And K is the number of available training snapshots that we use for training purposes. Okay, so let's talk a little bit about projection-based model reduction. I want to start off by recognizing that these problems are still very challenging, and there's really two main reasons. First of all, most existing model reduction techniques, they are intrusive in nature. Now, for some simple problems, that is fine, but in a broader setting, you won't always have access to, the source code that produce a set of training data, or you may not have access to the operators that are used in generating that data, right? Some codes are proprietary, and things like that, for which it means that, non-intrusive models are quite fundamental in developing reduced order models. Secondly, linear dimensional reduction, which is what a lot of the existing methods kind of build upon, they're very limited in the accuracy that can be achieved with reduced order models. We're clearly not the first one to make these observations, right? This is, I would say, quite well known within the community. And a lot of people have proposed different remedies for addressing these issues. First of all, there's a host of what I call problem-specific methods for these problems, like infection-dominated systems or multi-scale systems, etc. There exists a host of online adaptive model reduction techniques and different types of interpolation methods that have been around for many, many years. There's this idea of dictionaries of reduced order models, where essentially you kind of construct local reduced order models, in state space, spatially, or in time, and then you kind of try to patch back together the original high-dimensional states. And finally, something that's been getting a lot of attention recently is the use of nonlinear manifold reduced order models. And the last topic is what I'll be talking about more today. So this brings us to my contribution, which is the data-driven learning of quadratic manifolds. But first, let's talk really quickly about linear dimensionality reduction, right? So for those of you who are familiar with this, we're talking about proper orthogonal decomposition, right? That's what engineers typically like to call it. But in essence, we're talking about principal component analysis in computer science. So these methods they're perfectly equivalent. So essentially our gamma, which is the mapping I introduced earlier, is given by the following functional form. We have a reference state, the sref, plus v times s hat, where again, the v is your POD basis matrix, and the s hat is your POD coordinate vector. So essentially what we've done, if you look at the black trajectory, we have projected it onto a low-dimensional linear subspace. And what's interesting is that, as we know, there's always an error associated with these types of projection, and that this error, you can actually explicitly compute what those errors are. In essence, what we find is that, you can take the norm of that linear projection error that we're going to call epsilon, and that is given by the singular value squared of the singular values that were not taken into account with the modal truncation. So essentially, those are the one from R, where R is reduced basis dimension, all the way up to K. So those are the non-zero singular values that are not they're not part of your modal approximation. So we can kind of write that epsilon a little bit differently here, where we have introduced the V-perp, which is your orthogonal complement to your linear subspace, which is the POD basis matrix. So in essence, they show that these projection errors lie in your orthogonal complement, which makes a lot of sense if you think about it. So this brings us to the notion of data-driven learning of these quadratic mappings. So as I mentioned before, there is a non-negligible error, the epsilon t, associated with these Galerkin projections, right? So for an arbitrary state, st, we can write it as the sum of sref plus v s hat, right? Which is again your linear approximation, your linear POD or PCA approximation, plus an arbitrary or non-arbitrary, an error term, epsilon t, that you don't really know too much about, right? So this is clearly very problem specific. What we're going to propose now is we're going to replace that error term by a Kronecker quadratic term. And the way we're going to do it is as follows. We're going to take that term, we're going to approximate it by v bar, multiplied with s hat, Kronecker with itself. And what's interesting now is that now we end up with an approximation where everything is known. We know our sref, something you choose with some insights into the problem. V and s hat come to you from the proper orthogonal decomposition. The last remaining component that somehow you need to approximate or determine is that v bar operator. And what we're going to say, okay, we don't know what it is, but we do know how to approximate it, and we can actually solve it by means of a very simple optimization problem. We're going to try to find that v bar, or essentially the nonlinear part in your quadratic approximation, such that this optimization problem is satisfied. And what that means is that this mapping operator satisfies the following equation here on the bottom, at least in the least square sense. So this has to hold over all the available training snapshots going from, the very first snapshot, your initial condition, for instance, all the way up to your last 1K. The equation may look a little bit messy, but actually what it turns out is that this is a very simple linear least squares problem. And the way you can see it is as follows. We can assemble what we call the data matrix, which is essentially, you take your projected snapshot data that is projected onto the linear subspace, you take the Kronecker product with itself, and you end up with the data matrix of dimension k times r squared. The v bars are your unknown set of vectors, right? That's what we're inferring for. And the epsilon t's, the epsilon transpose, that's essentially your linear projection error. And we exactly know how to compute this. So this whole system is overdetermined if k is larger than r squared, which gives us at least a lower bound on the number of available training snapshots that we're going to need for this procedure to work. But in practice, we'd never really run into this issue. This problem decomposes into n independent linear least squares problems, right, where you each solve for a vector of length r squared. And what this means is that this whole approach can be treated in an embarrassingly parallel fashion, which means that all the linear algebra is highly scalable, as I will show later on. So to quickly summarize, what have we done up to this point? The only thing we've done here is we have learned a more expressive mapping from a set of high dimensional system states, right, for these dynamical system models, to a low dimensional embedding using that linear projection error as the driving mechanism. So because this is linear least squares, we can solve this problem explicitly in closed form using the normal equations. Again, it takes a little bit of linear algebra, but you're going to have to take my word for it. And we find the following expression for V bar. And what's interesting is that you can see that V bar lies in the column space of V perp. That I remind you is your orthogonal complement of your linear POD basis matrix. And what's really cool about this is that this gives you an orthogonality condition of V and V bar. In essence, that V transpose V bar, and the other way around gives you exactly 0. So the columns of these matrices are orthogonal. And that's a property that's going to turn out to be very useful if we're going to learn physics-based reduced order models, which will be the middle part of my talk. Typically these methods are kind of prone to overfitting. So we use regularization to deal with that a little bit. We have looked at standard Frobenius regularization. It actually turns out to work really well. And the second formulation we've explored, at least a certain degree, is the use of these group sparsity promoting algorithms that Stephen helped us a lot with. And what it does, it kind of forces some of the columns of what would be that operator V bar to be 0 to really deal with the data in a more efficient manner. So now I want to talk a little bit about the optimality of this approximation. In essence, the question we're asking is the following. Can we pose this manifold learning problem to learn V and V bar and the latent space representations S hat simultaneously? So I recall that this is our quadratic approximation. Sj is S ref plus V S hat plus V bar, and then S hat Kronecker with itself. We can essentially take an agnostic approach. We're going to try to find the V bar, and S hats without knowing anything. We don't know anything about POD. We don't really know anything. The only thing we have available is a set of training data. You can actually simplify this problem a little bit into the following form. It does result into a nonlinear constrained optimization problem that is quite challenging from a numerical standpoint to deal with. So that's not what we're going to end up doing today. But I at least want to show you how the approach that we talk about today kind of naturally follows from this exact nonlinear constrained optimization problem. If you look at the linear fit terms here, This is essentially your POD approximation. And we can exactly set this term to 0 by doing POD. This quadratic fit term, that's essentially the learning problem that I've talked about in the previous slide for inferring that operator V bar in an optimal fashion. So what the conclusion is for this is that the proposed approach is actually an approximation to the solution of this very messy looking nonlinear constraint optimization problem. But what I will say is that recently we have developed an algorithm that can actually solve this constraint nonlinear optimization problem in a very elegant fashion. So that's something I'm not going to talk about today. We're currently still working on a paper on that. But I will say you could take the POD route or you could take the direct optimization route. Those approaches are, going to give you some differences in performance, but actually both turn out to work really well. A lot of linear algebra up to this point. Let me give you a very simple, concrete example. We have a three-dimensional trajectory parameterized by a variable t, right, in a range 0 to 2 pi. The trajectory is cosine t, sine t, cosine 2t over 2. So in the plots, that's essentially the black curve here. Now what we're going to try to do is we're going to take that trajectory, project it on a two-dimensional subspace. From that, try to go back to reconstruct our original three-dimensional trajectory. If we do that with POD, you kind of do a projection onto a linear subspace kind of spanned by the two dominant singular vectors of that data matrix. And you see that, this does invoke a pretty large projection error. So that's just what it is. That's kind of what, not too surprising with these types of POD approaches. But on the right, you have the approximation that you end up with our manifold approach. And what it does, it kind of induces this curvature onto the linear manifolds to give you a trajectory that's a lot closer to the ground truth than you would be able to with the POD approach. So in a nutshell, this is really how this data-driven manifold gives you much more accurate state predictions. So now we want to use those state predictions in the context of projection-based model reduction. And our particular flavor of model reduction, right, because there's a host of approaches, is the opera inference approach. And one way to think about it is that this kind of is a blend of model reduction and machine learning. And instead of giving you all the technical details, I'll just quickly walk you through the algorithm of how in practice we kind of infer low-dimensional reduced order models, because the approach really is quite simple in nature. We start off with a snapshot matrix, right, dimension n times k. We compute the proper orthogonal decomposition to compute a set of basis vectors, right? So we end up with a v of dimension n times r. It's nothing surprising at this point. We do a projection of our training data onto that reduced space. So our S hat is given by V transpose S. Now what we're gonna do is assume we have a linear quadratic system, right? So we have a constant, linear, and quadratic, plus possibly an input term. We're gonna try to find the operators, the C hat, A hat, H hat, and B hat, such that this residual, such that this approximation holds in the least square sense by minimizing the following residual. So in essence, this is a model reduction approach, and the only thing it needs is the structure of the governing equations. And actually, quadratic structure is something that a lot of physical and engineering systems naturally admit, or they could be what we call lifted into this particular quadratic form. And then we're going to try to find a nonlinear reduced order model, right, characterized by these low order polynomial terms, such that this whole problem is minimized in a least square sense. So again, the only active ingredients we need for this approach is a set of training data and knowledge about the structure of the governing equations. We don't need intrusive access to those operators, we just need to know their structure. So that is why this approach is inherently non-intrusive, as was, so this was pioneered by Karen Wilcox, my advisor in UT, and Benjamin Pearsoffer, who is now in Courant. This is kind of what these methods buy you in practice. I'm not an expert on this particular rocket combustion problem. So this is something my colleagues here, particularly Shane McCory, has worked on. In essence, it's a rocket combustion problem, very complicated physics. We have pressures, we have temperatures, we have all kinds of chemistry going on at multiple scales. And to these systems, we now want to build a reduced order model, which is physics informed. Our training data has dimension about 300,000 degrees of freedom spatially, right? There's many different variables to keep track of. So these problems are quite large scale, and our reduced order models only have in between 20 and 100 degrees of freedom, depending on the amount of accuracy that you need. With our upper inference approach, we achieve almost 6 orders of magnitude speed up in the computational costs, which should be pretty compelling for you to start using these approaches, and they enable rapid future state predictions. So we do the training in a limited amount of training data, and then we can start making predictions about into the future about the dynamics of, for instance, the temperature field or the pressure fields. So now this was the vanilla approach with linear dimensionality reduction. How does this translate when you start using these nonlinear dimensionality reduction techniques, these quadratic manifold constructions? So to consider that, we're going to start off with a very simple linear system, right? After spatial discretization, which can be written in the following form. We introduce our low dimensional approximation for ST, right, which is the gamma of S hats, and we do a multiplication, what we call the left projection matrix, which is the phi here, to kind of give you the following system. The left projection matrix, we're going to choose it to be the linear POD basis matrix, because then what that allows us to do is we can exploit the orthogonality condition that I mentioned earlier on. So what this does, it gives you a reduced order model that has that linear quadratic structure. And what's really fun about this quadratic term is that it should be interpreted as a data-driven closure term, because you can actually infer it in closed form what it is. That essentially is given by V transpose A V bar. And again, the V bar, the columns of V bar are directions into the orthogonal complement of your linear basis matrix. So again, let's remind ourselves what we've done. We've started with a high dimensional linear model, right? It's very expensive to solve. We have introduced our quadratic approximation using our data-driven manifolds, and we end up with a reduced order model that has quadratic structure. So we have one extra term. We're gonna learn the operators, this model, the C hat, A hat, and the H hat with the operator inference framework and a non-intrusive framework. So end to end, we have a non-intrusive framework. We do the learning of the manifold approximation in a non-intrusive fashion, as well as the specific reduced order model. With a linear subspace approach, essentially this is the vanilla operator inference approach, which for linear problems is very closely related to dynamic mode decomposition, for those of you who are familiar with that, but in a time continuous formulation. It's the following form. It's a linear least squares problem that is very tractable from a computational standpoint. With the quadratic manifold approach, it is basically the exact same active ingredients. It's still the regression, over a set of training data. The only thing we need to infer now is this additional operator H hats. But again, both, these operator inference learning problems can be treated in embarrassingly parallel fashion. So this makes it very scalable as well. A quick demonstration of the approach. We have linear transport in 1D. By all means, this problem is considerably more challenging than you may originally anticipate because it is, transport in its fundamental nature. We have an initial condition that is this kind of Gaussian bell shape. For this particular problem, we know the exact solutions and our time derivatives in closed form, which is something we're going to exploit because it kind of eliminates any errors from a numeric standpoint. We construct a training data set by sampling the exact solution in space-time. We have 2 to the 12 degrees of freedom in space, 2000 snapshots, some model constants, and we do the training data. We do translation of the training data by means of its time average mean value. And then for testing purposes, we generate 50 more initial conditions over which we're gonna make an assessment of the quality of our reduced order model. The singular values are plotted here on the left, the normalized ones, and you can see clearly that they decay very slowly. So for any model production approach, this is very challenging because it implies you need many POD modes, or for the deep learning folks, you would need a very deep neural network in order to give your model some kind of accuracy. On the right, we have the snapshot energy metrics. With the linear manifolds, the expressions given on the bottom here is essentially, the sum of the singular values squared over all the available singular values squared. With the linear manifold, you start accounting for 100% of the energy as soon as you go to 40, 50 POD modes, which again is quite well known for standard linear dimensionality reduction. However, with quadratic manifold approach, you still need quite a bit of POD modes to kind of converge towards 100% energy, but it does trend to 100% energy kind of for much more rapidly than linear approaches would be able to do. What's interesting here is that there is this nonlinear dependence on the singular values. So it no longer gives you this nice summation, but we can devise this snapshot energy metric by means of evaluating this particular metric. So the singular values is still the driving factor, and that is implicitly represented into this equation. So this is what the solutions look like for different snapshots in time. The exact solution is given by the black dots. The linear manifold models are, standard POD approaches are given with the blue curves. I think this was about 30 POD modes, something like that. With the linear models, you will have this kind of Gibbs type phenomena, which again are quite well known. And the amplitudes of that moving peak are quite off. With the manifold approach, quadratic manifold approach, we do considerably better in suppressing these Gibbs type phenomena. And at the same time, we are much more accurate in capturing the amplitudes of that moving initial condition. If you start ramping up the number of POD modes, and eventually, these methods will both start looking really good. But for any given computational budget, we actually found that the manifold approach seems to work considerably better than the linear approaches. We can actually quantify these errors a bit more exactly. So we have the following error indicator. With the linear manifold approach, you have the black curves here. You see as you have about 60 POD modes, then you're within about 10% error for the reconstructed models, for the reconstructed states. Whereas with the quadratic manifold approach, you kind of achieve that level of accuracy, which is half the number of POD modes, so R is 30. With the quasi-quadratic manifold approach, so what that refers to is the sparsity promoting formulation of the approach. You have a little bit of a trade-off. So these models are considerably more efficient than the fully quadratic constructions, but they're not quite as accurate. So at least what this does, it kind of gives the user the flexibility of kind of trading off accuracy versus computational costs. Let's look at some more interesting problems. This is the wave equation, two-dimensional problem, about 500,000 degrees of freedom spatially. Again, our initial condition is this kind of Gaussian profile that now starts propagating. You kind of have multiple wave reflection events at the boundaries and all kind of interference events. So that's what we're trying to capture now with our reduced order model. With opera inference, the linear dimensionality reduction framework, it actually does seem to work quite well. I was actually surprised at how good this looks at just 40 POD modes. But you can see that the amplitudes are again quite off, and there's all kind of non-physical behavior away from the wavefront that ideally you would like to eliminate. With the manifold approach, we do exactly that, right? So the amplitudes are captured much more accurately, and these non-physical behaviors away from the wavefront are kind of suppressed. We can also look at the absolute error in the states at different time snapshots. With the linear model, which are the curves on the top, you can see that there's a lot of structure in those error plots, right? With the quadratic manifold approach, it kind of eliminates all the structure. Still, surely there is some error in the state approximation, but those error is a lot more high frequency than you would be able to do with the linear manifold approach. So this is kind of what this looks like for linear problems. I'm gonna shift gears a little bit, kind of step away from this path, and I want to give you a very simple extension to nonlinear problems. And for the folks on the call who are familiar with DMD, this is gonna look very similar in spirit. Nonetheless, this still explicitly relies on our data-driven quadratic manifold constructions. Now we're going to take a slightly different approach in that we are completely agnostic to the physics of the problem. We do not have any insights into the governing equations or, the process that was used in generating a set of data. We're going to talk about possibly some experimental data. So in essence, we're just going to say that we have a dynamic systems model of the following form, where at any given time j plus 1, we have a nonlinear transformation of the solution at the previous time step j. We're then going to proceed by arranging a set of training data into the data matrices, right? So essentially, this is the standard DMD approach, where you have S and S prime, where essentially the data is shifted by means of one time step. What this allows you to do is to build the so-called locally linear dynamical system by solving the following optimization problem. So again, obviously for large-scale problems, this is just computationally intractable and something we definitely do not want to do. So instead, what we're going to do is we're going to compute A tilde, which is the L by L projection of A onto the subspace spanned by the first L nodes of that of the data matrix S. And actually, you can kind of compute that in the following fashion, in a very straightforward fashion, just by means of doing singular value decompositions. Now, what we're going to deviate from DMD, what we're going to do is we're going to say that L, we're going to choose that as the rank of that data matrix S to effectively end up with this locally linear dynamical system. Sj plus 1 tilde equals A tilde S tilde j. Where again, clearly, because we are talking about POD, Sj tilde is the representation of the j snapshot in the POD coordinate system. What we're going to do now is we're going to introduce an additional dimension reduction, but now we're going to compute a rank R SV decomposition of that projected snapshot data S tilde. And that's given by the following form. And actually what this shows you is that S hat can be computed as, taking the concatenation of the identity of size R and then the zero matrix of size L minus R of VL transpose S. And what this does, in essence, it takes the dominant L POD modes that are embedded in that larger POD basis matrix VL. Because now there is an error associated with doing this projection, very much like in the previous approach, we are considering a quadratic state approximation of the following form. So we're going to say Sj is given by phi r Sj tilde plus phi bar Sj hat Kronecker with itself. What we now can do is, again, we know everything in this approximation except for the phi bar. We're going to try to infer that from the data by solving the following optimization problem. So again, this is exactly what we've done in our previous approach. Even now, we're kind of considering this two-stage dimension reduction for building nonlinear reduced order models. And what's interesting from our previous approach is that now this manifold learning problem is posed in a subspace of the original state space. So the whole dimension of this object is L times R squared. So this object no longer scales with the full state dimension N, which is a fundamental difference with our previous approach, other than the fact that we're actually trying to apply it to nonlinear problems. So by inserting this quadratic approximation, right, and again exploiting the orthogonality condition I talked about earlier, the Gellert reduced order model takes the following form. So we have our S hats that is given by a linear part A hat Sj hat plus a nonlinear part H hat Sj hat Kronecker with itself. And once again, we have a linear part and a nonlinear part, where the nonlinear part now has these directions in the orthogonal complement of that POD basis matrix that's naturally embedded in the approach. What's different here is that these matrices, the A hat and the H hat, they are computed explicitly. There's no need for any non-intrusive learning algorithm like opera inference or anything of that nature. We know A tilde, that is step one in the DMD, that locally linear dynamical system. We have computed that explicitly. So even though we end up with a nonlinear model, we have heavily relied on that locally linear model to kind of inform the structure of this nonlinear local reduced order model. So what's different from our previous approach is that clearly it applies to nonlinear problems of arbitrary complexity, no issues around scaling of the data matrix or anything of that nature, because again, these matrices are computed explicitly. The data-driven learning of this manifold approximation is done in a subspace, which makes it computationally much more efficient. And as I mentioned earlier, there's no need for opera inference or any other learning techniques in inferring the reduced order matrix operators. So what does this look like for a very simple Burgers equation? On the left, we have a reference solution, right? Where, we have an initial condition, I think it was a sinusoidal function that kind of evolves in space and time. We have trained up to time 0.1 on the y-axis, where the red line is. And after that, everything is purely predictive. With the DMD, you kind of see this kind of periodic behavior in time that, the original model doesn't really naturally admit, but the DMD kind of gives you this kind of periodic behavior because of its linear nature. With opera inference, the vanilla version, it does quite a bit better because the reduced order model has quadratic structure. It's still not quite what it should be, but it's considerably better than DMD. And with the proposed manifold approach, we kind of nail it on the spot. You still end up with a quadratic reduced order model, very much in DMD, but the terms have fundamentally different meaning because one is a manifold model whereas, the third model here is just a linear subspace model. So that really explains the differences in both these quadratic models on the right. Another really cool scenario for this particular approach is learning from experimental data. And specifically, I want to talk a little bit about this example, that is the use of particle image velocimetry data, which is something I've been working on with a colleague here at UT. Essentially, what they're trying to do is compute a reduced order model, or develop a reduced order model for hovering helicopters, and specifically the fluid structure interaction of the rotor blades with the air. Typically, in practice, what people do is, actually compute the CFD models, which, as you can imagine, is extremely computationally challenging. So for that, we essentially want to develop these reduced order models that can be used in real-time applications, like developing control for these types of systems. So the experimental data is given on the left, right? It's noisy data. You can kind of see the vortices kind of moving through the screen. Periodically, you will see kind of the tip of the rotor blades kind of moving through the screen. And on the right here, you have our proposed manifold approach. This is, just to be clear, this is purely predictive. We have done some training on, the training data that was provided to us by our collaborators, and we're trying to make future state predictions about, what the flow fields are going to look like at the tip of the helicopter blades. We've only done this with just 75 degrees of freedom, and we have about 63,000 spatial measurement points. This approach, again, we found it to be working considerably better than DMD and the vanilla operator inference, which is something we were quite excited about. So the idea for this work is that we're going to try to develop parametric reduced order models, in that, for this particular setting, we want to change the angle of attack of the blades a little bit, and kind of see, how it affects the flow fields, right, was essentially the thing we're going to need in order to develop efficient controllers, and try to infer structural loads on the rotor blades purely from this experimental data. This brings me to my final slide. I talked about a lot of different things, but we essentially have developed a data-driven approach for nonlinear dimensionality reduction that relies on what we call quadratic manifold constructions. These models are easily human interpretable, right? Everything I talked about today was in the space of linear algebra. There's no need for any deep learning techniques, etc. They enable rapid future state predictions, right? Because the surrogate models are extremely low dimensional and can be evaluated in a matter of seconds. And they're fully non-intrusive in nature. As I mentioned on multiple instances, the only thing we need is insights into the structure of the governing equations and a set of training data. For the second approach, the only thing we need is actually just data, because the model is physics agnostic in nature. We have shown the seamless integration within the operator inference framework, right? So one part was dimensionality reduction, one part was the physics-based learning of reduced order models. We have shown that these models can produce stable and predictive reduced order models with improved efficiency compared to anything in the linear subspace. And this idea of, these data-driven manifold constructions is, I think, quite powerful, and has opened up many different avenues for future research. One of which is, to use in a DMD spirit for nonlinear problems. We're currently also looking at polynomial manifold constructions and things of that nature. So we're quite excited about where this is all trending. And finally, I have a shameless plug for our CMAME paper that came out, I think it was 3-4 months ago in CMAME, that really talked about this approach and all its mathematical gory details in detail. And there's a couple more papers in the work along these lines. But nonetheless, I want to thank you for your time and attention, and I'm happy to take any questions or comments you have.
Super. Thank you so much, Rudy. That was really exciting work. We have a speaker.
Thank you.
We have a question already. Should I read it out too?
Yeah.
Okay, so we have a question from Lorenzo, who asks, how do the methods you showcase compare to neural operator methods and pins, which naturally offer quite effective learning capabilities for nonlinear problems? Any particular advantage or disadvantages?
That's a great question. We have not benchmarked it compared to any neural operators or pins type approaches, really anything in the space of deep learning, right? There's more approaches than, the two you mentioned. So I can't really comment on how well it compares. This really comes from the standpoint of projection-based model reduction, right? So we're not trying to replace existing PDE solvers like a pins approach would typically do, at least in my understanding. This is really focused on developing low-dimensional projection-based reduced order models where you can kind of exploit all the physics that you have. So that's the long answer. The short answer is no, we don't really have any good comparisons at this point. One thing I will add to that is that, as I mentioned in my final slide, our approach is human interpretable. So there's no need for assessing a neural network where the interpretability in some settings can be questionable. The only thing we end up with is low order dynamical systems that have polynomial structure, and everything naturally follows from the linear algebra. So that is, to me at least, the most appealing advantage, at least from a mathematical standpoint.
Thank you very much. Do we have any other questions? We have 3 minutes. If not, I have a question, if that's all right. Can you comment about generalization? So with regards to the quadratic manifold approach, can you comment about generalization in future states? So when you fit, the manifold, when you infer the manifold, of course, it is somewhat depending on the data that you have. How does that generalize for further time steps, and how far can you go? In other words, are you capturing the governing manifold?
That's a great question. You're not going to be able to do better than the training data that was provided to you, right? So if there's some events into the future that were not accounted for in the training data, there's just no way that the manifold can possibly account for that. So that's not a property of the manifold work that I've talked about today. I think that is more broadly applicable to projection-based model reduction.
Yeah.
But what I will say is that these manifolds, at least for the Berg's equation, like I've shown, we're currently looking at some rocket combustion examples that I also briefly touched upon. But what we did find is that they kind of tend to generalize quite a bit better than linear subspace approaches. So I can't really comment as to how broadly these observations are applicable and to what degree it applies compared to any other existing approaches. But for what we have seen, there are significant improvements to be gained using these data-driven manifold constructions.
Yes, thanks a lot for that. And I appreciate that the focus of the study of the work is in comparison with linear approaches. So thanks for your reply. So do we have any other questions? All right. If it's all right for you, Rudy, it would be great if you could share your slides. If not, that's also okay.
Yes, absolutely, no problem.
Fantastic. We will just, for those who are listening, we'll upload them to our website as we do for all speakers, and that would be a nice way to share with the community and also advertise your work.
Thanks so much for having me. This was great. This was fun.
No, it's a real pleasure. And again, I particularly enjoy this kind of research. So for me, it was a treat.
I'm happy to hear that. Happy to hear that.
Thank you. All right, so I won't keep anyone any longer, and you can get back to maybe having a nap. Thanks a lot. Oh, thanks, Said, for the nice comments. We will be with you in a couple of weeks. So until then, have a great day.
Thanks, everyone. Have a good day.
Bye-bye. Thank you.